So this question here asks us to find the inverse Laplace transform of this function here, f of s. 4s plus 8 divided by s squared plus 2s plus 10. Now, the limit of this function here as s approaches infinity approaches 0 because we've got a higher polynomial in the denominator than the numerator. So that's good to see. So usually from here we try and do partial fraction decomposition. But s squared plus 2s plus 10, we're not going to be able to break that apart. There's no factors in there without using the quadratic formula. Now that's not really going to work for us. So there is another technique we can use where we can find the square of our denominator. So if I let my f of s equal p of s over q of s, my q of s, let's just concentrate on that for the moment. Q of s, taking the square, that would be s plus 1 squared, so that'll be taking care of that. Then subtract a 1 from here because we've created another 1, so then we're left with plus 9. So that's my q of s. So now I can write my f of s now as 4s plus 8 divided by s plus 1 squared plus 9. Okay, that's still the same value as what we originally started out. So that's good. Now, one way we can go for now when we've got a square in our denominator is to use a general result. So if we have c times s minus a divided by s minus a squared plus b squared, this one will give us c times e to the at and cosine of bt. That's a general result for that one there. And then there's another general result which we could try and aim for, where we have c times b over s minus a squared plus b squared. Now that one will give us a general result of c e to the at and then sine of bt. That's a general result which we'll kind of try and look for our f of s. So either this one, or maybe both is going to be in our solution. So let's have a look at that. So we've got 4s plus 8 over s plus 1 squared plus 9. So s plus 1 squared plus 9, well, that's in the format that we like for our denominator. We could definitely use that. So we'll have a equals minus 1. So let's just write that here now. A equals minus 1. And our b squared equals 9. So therefore our b will equal 3. Okay, now our constant c, we're not sure where we are just yet. So we'll have a look at that. So we want an s minus a and an s minus a squared. Well, we've got s plus 1 squared here. So if we put an s plus 1 in our numerator, that will give us something that we can work with that. So let's do that. So if we took an s plus 1 out of that and then multiply that by 4, that gives us 4s plus 4 with just 4 left over. So that's valid for our numerator. And then we've got 4s plus 1. So we've got something here with a c. And then we've got a plus 4 here. So that could be something we could work with on this one. Okay, let's have a look what we can do here now. So we've got s plus 1 squared plus 9. Okay, now what we can do now, we can break this fraction apart and then we'll have either of these together. So now we've got 4s plus 1 over s plus 1 squared plus 9. And then we can add 4 over s plus 1 squared plus 9. So that's valid for that as well. So this, all that algebra, we're still in the same value as what we started with. So that's great news. Okay, so now what we could do is we could try and use these inverse Laplace standard transform results with these. So let's just break these up into that. So now our inverse Laplace of f, that equals the inverse Laplace. Let's have a look at this one. So 4 times s plus 1 squared plus 9. So we can bring the 4 out to the front, that's valid, and then we can leave the rest of the fraction inside the transform. So s plus 1 over s plus 1 squared plus 9. So that takes care of that one, and we've got something similar to this. This one here, let's do the same. So there's a 4, which is a constant which we can bring out. And then we got the inverse Laplace of 1 over s plus 1 squared plus 9. Okay, so with a equals minus 1 and b equals 3, we've got something similar here, but we've only got a 1 in our numerator. So we need a 3, so for this to be a valid transform. So let's put a 3 in the numerator. And then what we do is, as we've increased the value by 3 on the inside of the Laplace transform, by linearity, we just divide the whole thing by 3, and then we've not changed anything. So that would take care of that. So now we've got our Laplace transform in the manner that we want it. We've got a 4, which is our c. So here c, I'll call that c1, that equals 4. That's this one. And here we've got c2, that's our second constant, that would equal 4/3. So now we're ready to write this in the format that we want on these results. So now this one, so our inverse Laplace of f, that would equal 4 times, so we're working on this one, e, now a is minus 1. So be careful to write minus t, and then cosine of bt. Well, b is 3 in both cases, so therefore we've got cosine of 3t. And then this one here, we've got 4/3 as our c2. And then working on this one, e to the at, again a is minus 1, so e to the minus t. And then sine of 3t. Let's write that as 3t. Okay, now that could be a valid result. I'm happy with that. But you could also write that as 4 cosine of 3t over e to the t plus 4 over 3 sine 3t e to the t. So that is also a valid result as well. So either of these will work as valid Laplace transform results. Okay,